So now I want to talk about the most general possible solutions that there are. So let's start with the most general possible linear first order differential equation. And that can be written as dy dx is some function of x times y equal to some other function of x. So one type of equation like this is called homogeneous equation, where r of x is equal to 0, and then dy dx is equal to minus p times y. And this we can easily solve with a separation of variables. So we get all the y's on one side and the x's on the other and integrate. And after the integral, we get some expression that looks like this. And we can write our general solution without knowing what the function p of x is, as y is equal to c e to the minus integral of p of x dx. Okay, so let's consider an example. So let's solve this differential equation. dy dx is x squared y. We can easily solve that by plugging p of x into our general expression, and we get y as c e to the x cubed over 3. Okay, but another type that's going to be more tricky is the inhomogeneous equation, where r of x is not equal to 0. So we have this differential equation to work with. And the general solution in this case, well, we can use integrating factors, as in the book, to do this. Well, you get a general solution that looks like this, e to the minus h, the integral of e to the h, r of x dx, plus some constant, where h is this particular integral of the function p. So as an example, let's solve this differential equation. Dy dx times 1 over x squared is equal to y over x cubed, or plus y over x cubed is equal to 1. First, we need to put this in standard form by multiplying by x squared everywhere. So the standard form version of this is dy dx is 1 over xy is equal to x squared. So this is an inhomogeneous differential equation, where p of x is 1 over x and r of x is x squared. And so we can immediately write down this integral h, which is the integral of p of x dx, turns out to be log of x. And then this other term, just to actually compute it out, the e to the h x squared integral turns out to be 1/4 x to the 4. So we can put these terms into the general solution, recalling that the general solution was this form. Then we get e to the minus log of x times 1/4 x to the 4 plus c. The e to the minus log of x is just 1 over x. And so the general solution is 1/4 x cubed plus c over x. That's our general solution for that particular case. So I want to talk now about some properties, some very important properties of homogeneous solutions. And these are really mathematically interesting and important. So say we have a solution y1, then it turns out that b times that solution is also a solution. And we can check this by plugging in b times y1 into our form for the homogeneous solution, and we indeed find 0. So it's also a solution as long as y1 is a solution. Similarly, if y1 and y2 are both solutions, then the sum of these two, y1 plus y2, is also a solution. So we plug y1 plus y2 into our expression for the differential equation. And since this is linear, this just turns into two versions of the original equation for y1 and y2. Also, y equal to 0 is always a solution. So those are some properties of homogeneous solutions. But it's useful also to talk about some of the properties of inhomogeneous solutions. So just to recall, those are differential equations where the function r of x is not equal to 0. A few things to note. One, if y1 is a solution, then b times y1 is not actually a solution. That's true for the homogeneous, but not for inhomogeneous. Similarly, if y1 and y2 are solutions, their sum is actually not a solution to this equation. And lastly, I think it's pretty clear that y equal to 0 is also not a solution to this equation. So what are the properties? Well, one of the properties is if y sub I is an inhomogeneous solution of the equation, and y0 is a homogeneous solution, then it turns out if you add these two, yi plus y0, then this is a solution to the inhomogeneous differential equation. Okay, so we took an inhomogeneous solution and a homogeneous solution, added them together, it's a solution to the inhomogeneous differential equation. We can see this by writing out the general solution that we had above into two terms, multiplying through. And it turns out there's one term which is the inhomogeneous solution, and then another term which is really just the homogeneous solution, just like we said in this property. Another property is if y1 and y2 are both solutions of the inhomogeneous differential equation, then if you take the difference between y1 and y2, this is a solution of the homogeneous differential equation. And just to write that out to see why this is true, if you take the difference of these two and plug it into the homogeneous differential equation, well, you get the difference of these two expressions, but each of these is equal to r of x, and so this whole expression is equal to 0. So the difference between y1 and y2 is a solution to the equation where r of x is equal to 0. So in summary, the general solutions to the homogeneous and inhomogeneous differential equations can allow you to solve a lot of different types of problems.